follows the frame.
That's so good.
Just goes. You can see the how much line.
All right, so we're going to talk about arc length. Arc length is just like we talked about when we talked about it in honors pre-cal. It's the length of a curve. Like in the where have we heard arc length before? Circles, haven't we? The arc length of a circle. You know, this is what this would be an arc length, yes? And we call it S. Arc length. Okay, so what we're going to do is we're going to apply that's the length of a curve. So I'm going to suggest that we have a function f of x equals the square root of 4 minus x squared. I'm sorry, no, we're going to make it simpler than that. Let's not take the square root of it. Let's just make it 4 minus x squared to make it easier. Make our derivatives less onerous. Okay, and I'm going to graph that. That's a parabola that's upside down, and the zeros are -2 and 2. And let's say I want to find the length of the curve from -1 to 2. So that means I'm going to have the length of this curve. I want to find the length from here to here. Everybody follow what we're doing? Now, I could estimate and suggest to you that I could estimate the length of this curve by finding this distance.
Oh no.
Well, now I know that stinks, but we're just going to throw it out there. What is this point here? If I plug in, it's -1, 3, yes. And this point here is 2, 0. And if I were going to find this distance here, or this length, it would be distance equals
Square root.
Good, of
Oh,
3 minus 2, quantity squared,
wait,
plus.
3 minus 2?
Oh, no, I'm sorry, -1 minus 2. Quantity squared, plus
3 minus 0.
3 minus 0, which is much nicer. So I'm going to say my arc length is approximately
2 or 3.
The square root of, I'm going to put that intermediary steps in there. Is that all right? So it's 9 plus 9, which is root 18, which is
3.
root 2. Which is what you said, I know, but I'm just.
I meant to say. You said 2. I said 2 or 3, but I meant to say 3.
Okay, somebody's got a calculator. You're going to tell me what this is approximately. Four, 2,
4.
4.
Oh no, 4.24.
4.24. I need 3 DPs for AP
2,
calculator.
4, 3.
Units. I could get better, couldn't I?
Make it 2 minus.
I could use this distance. Oh my goodness. Yes, I like that. This is what point here? 0, 4. So I can say the arc length estimate number 2, this is arc length estimate number 1, is approximately the square root of, okay, so now let's do the distance between this point. This is -1 minus 0, quantity squared, plus
3 minus 4 quantity squared.
3 minus 4 quantity squared plus the square root of 0 minus
2.
2 squared
4
plus
minus 0.
4 minus 0 squared which is approximately, that's going to be 1 plus 1 is root 2 plus, that's going to be 4 plus 16, which is
20.
2 root 5.
which is 2 root 5, yes. Now somebody's going to tell me what that is.
5.886.
That's approximately 5.886 units. And of course, which one is a better estimate?
The second one.
The second one.
Quite a bit of discrepancy.
There is. And I can get better and better by doing what?
Integral.
You do
Sum of the
Doing-
limit.
Infinitely many
Line.
segments.
Yes.
All right, well, let's suggest that one of my segments be right here. I'm going to call this DS.
How do I feel like we're about to do the integral of the derivative?
So I'm going to say DS equals, now I'm going to pull this DS out right here. Down here, that length right here. I'm going to bring it down here. We're going to analyze it a little bit. Could I say that this is something squared plus something squared?
X squared
Sure.
plus Y squared.
Well, not necessarily X, but this is a little bit of the arc length, infinitesimally small amount of the arc length. So what would this be? Infinitesimally, be little dx, yes. Quantity squared plus, using Pythagoras, little
YX, DY.
dy. Quantity squared. Agreed?
Wouldn't that have to be?
This would be dx, and this would be dy.
Or wouldn't that be DS squared? Like X
Oh
squared.
yeah, it's squared. I'm sorry, yeah. You bet. And then little ds would be equal to the square root of dx squared plus dy squared. Do we agree with that? And now what I'm going to do is in this, under the square root, I'm going to factor out a dx squared.
Wait, what?
I know. But you're going to see why in a minute. So what happens when I factor a dx squared out of the dx squared? You get 1 plus
dy squared, dx squared.
dy squared over x squared.
So
How
I'm not sure
come
why
you
one's
wouldn't?
squared.
So this is written the same way. Would you agree with this?
This one
It
looks
looks
like.
like I wish it were one.
No, we're not even there yet.
It'd be
I
so cool if
appreciate
they
you
tied
thinking of that yet. What was your question?
How come you wouldn't like take the derivative of y to make it dy?
That's what I'm doing is coming up with a formula so that
Okay.
you will be able to do that,
Okay.
right? All right. But I can take the square root of dx squared, yeah?
Yes.
And I could relocate it to the back. So I can suggest that a small, infinitesimally small piece of the arc length is going to equal the square root of 1 plus the derivative of your function squared times
Yeah.
the little piece of dx. But I don't want just a little infinitesimally small piece of the arc length. I want
All of them.
all of it. So I'm going to integrate I'm gonna sum them all up from A to B of the square root of 1 plus dy dx quantity squared dx.
Same thing, like in terms of y.
Yes, you can.
Why would you do
Yes,
that?
that's a great question. So our book calls arc length L for length, but F unit is S. Okay? Yes.
Would A to B in that case be like the -1 and 2?
Yeah, we're gonna do it right now. So
Okay.
now we have a formula for it. So let's see if we can find the exact length of that curve. So we're gonna say L equals the integral from -1 to 2, because that's what we were trying to find. The square root of, well, 1 plus, well, what is the derivative of our function?
-2x.
Right, dy dx here is, or f prime of x here is -2x. Do we agree?
Yes.
So we're going to take that and put it right here and say -2x quantity squared dx. And this is equal to the integral from -1 to 2 of the square root of 1 plus 4x quantity squared dx. And you have to use a technique called trig substitution to integrate this, which is not in our curriculum. So we're just going to use a calculator to do it right now. So the arc length is going to be about, so put it in there and see what you get. The more practice you do on the calculator, the better you'll be. The quicker you'll be. Yes, sir.
Can you scroll up a little bit?
Further?
I think I missed the part where you're saying like, what's dy over dx? Can we get that?
Okay, if I'm squaring dy and I'm squaring dx, may I, if I'm doing this, may I suggest to you that this is the same?
No, yeah, but like how'd you get to that?
Oh, I took the
That
derivative
is
of my function, but I'm
nasty.
right, I'm sorry, yes.
So we got
And we got -2x. When you take the derivative of 4 minus x squared, which is our function, you get -2x.
Okay.
And that's what goes there. And what did you get?
6.126.
6.126, based on what we observed. It's not units squared, it's just units. Just based on what you observed, our first estimate was,
4.243.
right, but it was on the low end. We knew it would be.
Right.
And then it got better.
Yeah.
Okay. So questions on that?
Why would you ever need to know arc length? Like, that's not meant to be like snappy. Just like, how would it be applied? Okay.
Yeah.
Should I have like the equation to put in?
Sure.
So it look like 1 mile from here, it's 2.5 miles of driving.
distance versus displacement.
All right. Now, Will asked a great question. He said if I go from A to B, the arc length was 1 plus dy dx quantity squared dx. What if I was trying to find the arc length, but I had x equals a function of y?
Dx, dy.
Yes, you can do the same thing with our formula here. And instead of factoring out a dx squared, you'd factor out a dy squared. And so what does that do? It changes the formula to 1 plus dx over dy. Yes.
Dy.
Dx over dy quantity squared, yes.
How would you find that derivative? We can just change it to
Yeah, put
x equals y and then solve.
X equals f of y.
I may have an example of that when we're doing it. But so I'm going to write, or what would we say? L equals the integral from c to d of 1 plus dx dy quantity squared dy. And that's if you have x equals a function of y. And you would just take the derivative of this I'll give you an example. So x equals, I don't know, y squared minus y cubed. So the x dy, the derivative of x with respect to y is what? You just take the derivative with respect to y over here, which is
2y.
2y minus 3y squared. You see the difference? That's all there's to it. Okay? It just depends upon what your setup is and what you were given in your problem statement. Okay? So let's do another example. Let's say we want to find the arc length. Now arc length just means length of the curve. X to the 3/2 from or over the interval 0 to
6.
4. 0 to 4. Okay, so let's do this a graph here. X to the 3/2. It's a power function.
It's a seagull. Or not a seagull.
Not-
A seagull.
No, it's not a seagull because
Oh, wait.
x1 is bigger than 1, but I like what you're thinking. It's in the first quadrant and it looks like this, right? Its domain is only on the right side because it's an even root. So I want to find this distance here from 0 to 4. Okay, so what do I need? I know I need dy dx, which is 3/2 x to the 1/2. And so my arc length says it's going to be the integral from 0 to 4 of the square root of 1 plus 3/2 x to the 1/2 quantity squared dx. Okay, now we can actually do this one. This is going to be the integral from 0 to 4 of the square root of 1 plus this is going to be 9/4 x. And we can integrate this using what method?
Calculator method.
Okay, the calculator method, that's funny, yeah. U sub. So we can let u equal 1 plus 9/4 x. Du equals 9/4 dx. So what am I multiplying my integrand by? 4/9. So this would be 4/9 times the integral of u to the 1/2 du. Now, why am I not plugging these here? The limits of integration? Because they're not defined in terms of u. I'm just going to use this as an integral technique here. So this is going to be 4/9 times u to the, 2/3 u to the 3/2. And I'm going to take it back and put it in my statement here. What do we get? We get, that's 8/27. And what was u? 1 plus 9/4 x to the 3/2 evaluated between 0 and 4.
I don't know.
So what happens when we plug 4 in? We get 10, don't we? That's not a very nice number, but it's 8/27. 10 to the 3/2 minus 1 unit. I mean, that's all you can do without a calculator. And if somebody would do that for me, we'll get an approximation.
Wait. Why do we have a -1? Do you need +1?
No, because what happens is when I plug in 4, I get 10, and then I go minus because it's f of b minus f of a, right? When I plug 0 in here, 1 to the 3/2 is 1 always,
Oh, the 8 minutes.
right?
Okay.
I'm sorry, what is it?
9.07.
You notice I have equals here and approximate here. Another example? We get it all? How about this one? We're going to find the arc length. This is your favorite.
E to the x.
So what do I need?
One dx.
I need dy dx. And let me ask you this. We need to know, right, if we're taking the derivative, if it's continuous. Is natural log of cosine x continuous between 0 and pi over 4?
Yes.
Well, cosine of 0 is
Continuous.
1, and then it's continuous, and then it goes to root 2 over 2. So is it going to hit any negative numbers?
No.
No. So we're okay. Okay, so this is going to be, what's the derivative of this?
Oh crap.
It'd be 1 over
Cosine
cosine
negative
x.
sine x.
Oh, no,
No, you never
negative sine x.
See, this is a nice little review of the chain rule of derivatives, yes. Okay, so the arc length is going to be the integral from 0 to pi over 4 of the square root of 1 plus tan squared x.
Isn't it negative tan squared?
Well, I'm squaring it. I'll show it in 2 steps.
I'm not complaining, but why didn't we draw this one? Just do it forward.
I'm not sure I know what it looks like.
Okay.
I mean, I'd really have to think about it. I know the cosine. Okay, so I know that the cosine of 0 is, and ln of 1 is, right?
Oh, yeah.
Okay, and then cosine of pi over 4 is root 2 over 2.
That's very good. Straight.
Well, cosine, okay, so cosine of pi over 4 is root 2 over 2, which happens to be a number less than 1, isn't it? Because it's 1.414 divided by 2. So it's less than 1, right? The log of a negative number, log of a fraction between 0 and 1 is negative. So I suspect
That gross graph.
it looks like something like that. If I had to guess.
It looks like that, Miss Miller.
Okay, but the piece we want is,
That.
well, I
That's
have the concavity wrong.
Yeah, but that's okay.
I mean,
That's
yeah,
what
that's not bad for not knowing what it looked like. Do you agree?
I agree.
Okay. So when I square that, I get what? L equals the integral from 0 to pi over 4 of the square root of 1 plus, yes, there are some graphs even I don't know what they look like, but we just have to use some analytical thinking, yeah?
Right.
Now, I don't know how to integrate that, but I do know that tangent squared is equal to 10. No, the opposite.
Secant squared minus 1.
That's right. Now, why am I happy about that?
One's
The ones get
So the ones cancel.
and it's secant squared. So it's just secant.
squared.
So this then turns into the square root of secant squared x dx, which is,
Doesn't that just force like that to be in like quadrant 1?
mm-hmm.
Okay.
Ooh, now how do I integrate that?
1
This
over
is-
cosine.
Seemingly bizarre factor of 1. Oh, Mr. Gannon was, yes. But are these things you need to know how to do? The answer is
Yes.
yeah.
Sometimes.
No. And so the seemingly bizarre factor of 1 turns out to help you figure out and create a u and a du. So what is my u in this case? Sec x plus tan x in the denominator. My du turns out to be the numerator. So if I let u equal sec and x plus tan x, du is secant x tan x plus secant squared x dx. And do you see how that's the numerator? So this turns out to be the integral of 1 over u, which you will agree that that's no big deal, right? That's just the natural log of the absolute value of u. Okay, so this turns out to be the natural log of the absolute value of secant x plus tan x, evaluated between 0 and pi over 4. Okay, so what happens when we plug in pi over 4? We get natural log of, well, that's going to be secant of pi over 4 is root 2. That's worth knowing, probably at your fingertips. Plus the tangent of pi over 4, which is nicely 1, minus the natural log of the absolute value of, well, the secant of 0 is just 1 over the cosine of 0, which is 1 or 1 over 1, plus the tangent of 0, which is 0. So then this just turns out to be what here? Natural log of 1, which is 0. So our answer is the natural log of root 2 plus 1 units. And if you do that on a calculator, I got about 0.881 units.
Something that complicated.
Yeah, sure.
We really don't get it to be easy in this class.
Well, okay, so 61% today. But by the time you get there, you're going to know how to integrate secant.
At
Trust me.
least we hope,
With all or nothing, you're going to know how to integrate secant.
or you get it nothing.
We're not going to get nothing. I do want to show you one. I'll put all of my notes online, but I do want to show you one, and it's number 28 from the book, which is root x plus root y equals 1.
This will take a lot.
So what happens when x is 0?
Y has to be 1.
Y is 1. And when y is 0, x is 1. So let's talk about the domain. The square x has to always be positive and y has to always be positive. So what quadrant does this live in only?
1.
1. And this curve looks like this, actually. Okay.
X y to get 0.
Mm-hmm. Okay, now,
That's a nice.
when I write the arc length formula down, we're going to go from A to B.
Wait, Miss Miller, is that the whole graph?
It is, I
Oh
think.
my gosh.
If I'm integrating from 0 to 1, anybody see a problem?
I'm guessing
Who agreed to this?
Derivative doesn't exist there, does it?
Mm-mm.
So if it doesn't exist there, you can't use it as an endpoint.
Limits.
What?
Limits.
So but it's looking pretty symmetrical, yes?
Yeah.
This graph?
Mhm.
So
do 2 times.
we could
Why was it?
use y equal x and figure out what this point is, and then do 2 times this distance and find out what that one is, right? So if you have a place where the derivative doesn't exist, you can't use it as one of your limits of integration. Yeah,
Why
Wait.
doesn't the derivative exist?
because you have a vertical tangent here.
Wouldn't the derivative not exist if the other one also?
Well, the derivative there is 0, isn't it? The slope is 0.
Oh,
Okay, so what happens to my equation if I let y equal x? If I have square root of x plus square root of y equals 1, this would be root x plus root x equals 1, 2 root x equals 1, root x equals 1 over 2. What does x equal? X equals 1/4. Well, guess what? Y also equals 1/4, yes?
yes.
So what is this point? This point is 1/4, comma, 1/4, which is not what you would expect, is it? You might want to expect it to be 1/2, right? It's not. Okay,
That makes sense.
so I'm going to find the arc length and go 2 times the integral from
1/4 to
1/4 to 1, yes. And then I have to have the square root of, well, I need dy dx. And I have root x plus root y equals 1.
1 minus root x equals root y.
So root y equals 1 minus root x. What does y equal?
1
The
minus,
absolute value.
Well, no, I'm squaring, right?
1 minus, oh crap.
Do you read that? Now I'm going to take the derivative of this. Equals, power down, function,
1
low
minus
to
root
power 1
x
times the derivative of the inside, which is,
minus 1/2 to the negative 1/2.
and I'm going to take that information and put it where?
Back
dy
in.
dx.
So this is 1 plus, now what happens when I square, these 2's cancel, yes, if I could simplify it a little bit. And I'm left with 1 minus root x over root x, and I'm going to put a negative out here. If that's all right. What happens when I square it? Does the negative go away?
Yes.
So this is going to be 1 minus root x over root x squared dx. Yeah, I would put that on the calculator.
That's juicy.
Yeah, and I didn't get a chance to do one that was dx over dy, but I will put an example of that on Moodle because I have one worked out, okay?
Is this on the quiz next class?
No, arc length
Good
is
afternoon,
not.
everyone. Let's prepare for afternoon announcement. There is only one.
Okay.
Clear and dismissal. Whoever Nora needs to stop at the front office immediately following announcement. Please stand for afternoon prayer.